Far from the warmth of the sun, orbiting the giant planet Jupiter, lies one of the most mysterious worlds in the entire solar system, the icy moon Europa. At first glance, Europa appears quiet and frozen, its surface covered in a vast shell of ice, stretching for thousands of kilometers. But beneath that frozen crust, scientists believe something extraordinary may exist. Data collected from missions like Galileo revealed strange cracks, ridges, and chaotic terrains across Europa's icy surface. These features suggest that the ice may be slowly shifting, breaking, and reforming over time, as if something deep below is pushing upward. Many researchers now believe that under Europa's thick ice shell lies a massive global ocean, possibly containing more liquid water than all the oceans on Earth combined. Hidden in total darkness, this alien ocean may be warmed by tidal forces created by Jupiter's immense gravity. If this ocean truly exists, it raises one of the most profound questions in science. Could life survive in the dark oceans beneath Europa's frozen surface? In this documentary, we will explore the mysterious ocean hidden beneath Europa's ice, the evidence that suggests it exists, and why this distant moon may be one of the most promising places to search for life beyond Earth. Far beyond the familiar blue oceans of Earth, deep in the cold outer regions of our solar system, orbits one of the most intriguing worlds ever discovered. This world is not a planet, but a moon, a frozen sphere circling the massive gas giant Jupiter. That moon is Europa. At first glance, Europa appears quiet and lifeless. From space, its surface looks smooth and pale, almost like a giant frozen marble drifting silently through darkness. Unlike many moons in the solar system, Europa has very few visible craters. Instead of being covered in ancient scars from asteroid impacts, its surface is marked by long cracks, strange ridges, and chaotic patterns stretching across thousands of kilometers. These mysterious features are what first caught the attention of scientists, because in the solar system, surfaces that remain unchanged for billions of years accumulate craters. Every asteroid impact leaves a permanent mark. But Europa is different. Its surface looks surprisingly young, almost as if the ice is constantly shifting, renewing itself, and erasing old scars. Something beneath the surface appears to be reshaping this frozen world. For decades, scientists wondered what could be happening under Europa's icy crust. Was the moon geologically active? Could there be heat inside such a small and distant body? Or was something even more extraordinary hiding beneath that frozen shell? The first major clues arrived in the 1990s, when NASA sent a spacecraft to study Jupiter and its moons. That spacecraft was Galileo. Launched in 1989 and arriving in the Jovian system in 1995, Galileo became the first mission to orbit Jupiter and study its moons in detail. Over the next several years, the spacecraft made multiple flybys of Europa, sending back detailed images and measurements that would change our understanding of this mysterious moon forever. What Galileo revealed was astonishing. Europa's surface is covered in an intricate network of cracks and dark lines that stretch across the moon like enormous scars. Some of these lines run for thousands of kilometers. Others intersect in complex patterns that resemble shattered glass. Scientists believe these features are caused by enormous stresses within the ice. Europa orbits incredibly close to Jupiter. only about 670,000 kilometers away. Because of this proximity, Jupiter's immense gravity constantly pulls on Europa. As the Moon travels along its slightly elliptical orbit, the gravitational forces acting on it change continuously. This creates a phenomenon known as tidal flexing. Europa is literally being squeezed and stretched by Jupiter's gravity. During each orbit, the Moon's surface rises and falls by dozens of meters. The ice crust bends and cracks under this stress, producing the long fractures seen across the surface. Over time, these cracks can open, shift, and refreeze, creating the complex patterns that cover Europa today. But tidal flexing does more than just fracture the ice. It also generates heat. The constant gravitational tug from Jupiter needs Europa's interior in a process similar to how repeatedly bending a piece of metal causes it to warm up. This internal friction can produce enough heat to keep the parts of the Moon's interior from freezing solid. This realization led scientists to consider a revolutionary possibility. If Europa's interior is being warmed by tidal heating, then beneath the frozen crust there might be a layer of liquid water, an ocean. The idea seemed almost unbelievable at first. Europa is extremely far from the Sun, more than 5 times farther away than Earth. At that distance, sunlight is weak, and surface temperatures drop to around minus 160 degrees Celsius. Under such conditions, any water exposed at the surface freezes instantly. Yet, beneath a thick, insulating layer of ice, things could be very different. Water ice is actually a surprisingly good insulator. If Europa's outer shell is thick enough, perhaps 15 to 25 kilometers, it could trap heat inside the Moon's interior. That trapped heat, combined with tidal heating, could allow liquid water to exist beneath the surface, a hidden ocean sealed beneath ice. To test this idea, scientists turned to one of Galileo's most important instruments, its magnetometer. This instrument measures magnetic fields. Jupiter possesses an enormous magnetic field that stretches millions of kilometers into space. As Europa moves through this magnetic environment, any electrically conductive material beneath its surface would interact with the field. Liquid salt water happens to be highly conductive. When Galileo flew past Europa, its magnetometer detected something strange. The magnetic field around the Moon appeared to fluctuate in a way that suggested the presence of a conductive layer beneath the ice. The most plausible explanation was a global ocean of salty water, an ocean potentially hundreds of kilometers deep. If this interpretation is correct, Europa could contain more liquid water than all the oceans on Earth combined. And that possibility immediately raised one of the most profound questions in science. Could life exist there? On Earth, life thrives in places once thought impossible. Deep beneath the ocean surface, far from sunlight, entire ecosystems survive around hydrothermal vents on the sea floor. These vents release heat and chemicals from Earth's interior, providing energy that sustains complex biological communities. In these environments, sunlight plays no role at all. Life, instead, relies on chemical energy, a process known as chemosynthesis. If similar conditions exist on the ocean floor, beneath Europa's ice, then in theory, life could survive there as well. The idea that an alien ocean might contain living organisms transformed Europa from a distant icy moon into one of the most exciting targets in planetary science. But before scientists could even begin thinking about life, they needed to answer a more fundamental question. Does Europa's ocean truly exist? To confirm the presence of a subsurface ocean, researchers began examining Europa's surface in greater detail. If an ocean exists beneath the ice, its movement should influence the crust above it. And that is exactly what the evidence appears to show. In many regions, Europa's ice surface looks broken and rearranged, almost like enormous floating plates that have shifted and rotated. These areas are known as chaos terrain. Chaos terrain looks exactly like what might happen if the pieces of ice broke apart, floated on liquid water below, and then refroze in new positions. Some blocks are tilted. Others appear to have drifted several kilometers before freezing again. This pattern strongly suggests that the ice shell may occasionally melt from below, allowing surface plates to move. Another fascinating feature on Europa's surface is the presence of double ridges. These ridges form long parallel walls of ice, sometimes rising hundreds of meters above the surrounding terrain. Scientists believe they may form when water from the subsurface ocean forces its way upward into cracks in the ice. As the water freezes, it expands, pushing the surrounding ice upward and creating ridges. These ridges may represent ancient plumbing systems that once connected the hidden ocean to the surface. Even more intriguing is the possibility that small amounts of ocean water may occasionally erupt through cracks in the ice. Observations from the Hubble Space Telescope have detected what appear to be water vapor plumes rising from Europa's surface. These plumes may be similar to the geysers seen on Enceladus, where jets of water shoot hundreds of kilometers into space. If Europa also produces such plumes, spacecraft could potentially sample ocean material directly without needing to drill through kilometers of ice. This possibility has energized scientists around the world, because if we can study material from Europa's ocean, we might finally learn whether life exists beyond Earth. In the coming decades, new missions will attempt to answer this question. One of the most important of these missions is the upcoming Europa Clipper. Scheduled to explore Europa in the near future, Europa Clipper will carry a suite of advanced instruments designed to map the Moon's surface, analyze its ice shell, and search for evidence of water plumes. The spacecraft will perform dozens of close flybys, studying Europa in greater detail than ever before. Its mission is not only to confirm the existence of the hidden ocean, but also to determine whether that ocean could support life. Because if life can exist in the dark oceans beneath Europa's ice, it would mean something extraordinary. It would mean that life is not limited to warm planets close to their stars. It could exist anywhere that liquid water, energy, and chemistry come together, even in the frozen outer reaches of planetary systems. Europa may therefore represent one of the most promising places in the solar system to search for alien life. A silent ocean hidden beneath kilometers of ice. A vast, dark sea warmed by gravity and geological energy. And perhaps, somewhere in that darkness, the first signs that life is not unique to Earth. The frozen surface of Europa looks calm and silent from orbit, but when scientists began studying it more closely, they realized that this icy world is far more dynamic than anyone expected. Beneath the bright shell of ice lies a landscape shaped by powerful forces that may be connected to the mysterious ocean hidden below. To understand Europa's hidden ocean, Scientists first had to understand the strange patterns covering its surface when spacecraft images began arriving from the Jovian system. Researchers immediately noticed that Europa's crust was unlike anything else in the solar system. Instead of impact craters or volcanic plains, Europa is covered with a network of long, dark streaks stretching across the entire moon. Some of these lines run for hundreds, even thousands of kilometers. These lines are called linea. From orbit, they look like giant cracks in the ice, as if the moon's surface has been repeatedly split apart and stitched back together. Many of these fractures intersect with one another, forming a complex web of geological scars. The most remarkable thing about these features is their scale. Some of Europa's fractures are wider than entire cities. Others appear to have shifted sideways by several kilometers, suggesting that large sections of the icy crust have moved relative to one another. This kind of movement hints at a flexible outer shell, one that may be floating above something softer beneath. Scientists believe the ice shell may behave like the frozen surface of an ocean on Earth. Imagine a large frozen lake during winter. As the ice expands and contracts, cracks appear across the surface. Pieces of ice can slide, shift, and rotate. When water refreezes between these cracks, it creates ridges and new patterns. A similar process may be happening on Europa, but instead of a thin layer of lake ice, Europa's crust may be tens of kilometers thick. Beneath that crust, however, the same principle could apply. A frozen shell floating above a vast liquid ocean. One of the strongest clues supporting this idea comes from the unusual double ridges seen across Europa's surface. Double ridges are pairs of parallel walls of ice that rise hundreds of meters above the surrounding terrain. Between the ridges lies a central trough or valley. These structures can extend for hundreds of kilometers and appear in many different regions of the moon. Scientists believe these ridges may form when water from the subsurface ocean rises upward through fractures in the ice. As tidal forces from Jupiter flex the moon's crust, cracks open in the ice shell. Liquid water or slushy ice from below may slowly seep upward through these cracks. When this water reaches colder layers near the surface, it freezes and expands. This expansion pushes the surrounding ice upward, forming the tall ridges we observe today. Over time, repeated cycles of cracking, filling, and freezing could build enormous structures across the moon's surface. In some places, the ridges appear to have collapsed or shifted, suggesting that the crust beneath them may still be slowly moving. This reinforces the idea that Europa's ice shell is not a rigid, frozen block, but a flexible layer constantly influenced by internal activity. Another fascinating feature found on Europa is something known as chaos terrain. Chaos terrain is exactly what its name suggests. A region where the ice crust appears broken into countless irregular blocks. These blocks are tilted, rotated, and scattered across the surface as if the ground itself shattered and rearranged. Some of these blocks are the size of mountains. Others resemble enormous floating plates that have drifted apart before freezing again in new positions. Scientists think chaos terrain may form when heat from below melts parts of the ice shell. When this happens, the rigid surface above loses support and begins to break apart. Large slabs of ice can then float on slushy water beneath them, slowly drifting before eventually refreezing. This process would produce exactly the kind of disrupted landscape seen in chaos regions. What makes chaos terrain especially important is that it suggests the ocean below may occasionally interact directly with the ice shell above it. In other words, the hidden ocean might not be completely sealed away. It may sometimes influence the surface itself. These interactions could even allow material from the ocean to reach the surface. If that happens, it would give scientists a rare opportunity to study the chemistry of the ocean without drilling through kilometers of ice. But Europa's geology reveals even more clues. Careful analysis of the Moon's surface shows that its ice shell has very few impact craters. This is unusual for a body that has existed for billions of years. Over such long periods of time, asteroid impacts normally accumulate and remain visible forever. Yet, Europa's surface appears relatively young. This means something must be constantly renewing it. The most likely explanation is that Europa's ice shell is gradually reshaped by internal activity. Cracks open and close, new ice forms, and old surface features disappears beneath shifting layers of frozen water. This ongoing resurfacing suggests that the Moon remains geologically active even today. But what provides the energy to keep Europa active? The answer, once again, lies in the immense gravity of Jupiter. Europa's orbit around Jupiter is not perfectly circular. Instead, it is slightly elliptical. This means that during each orbit, the distance between Europa and Jupiter changes slightly. When Europa moves closer to Jupiter, the planet's gravity pulls more strongly on the Moon. When Europa moves farther away, the pull weakens slightly. This constant change causes Europa to stretch and compress during every orbit. The Moon literally flexes like a rubber ball, being squeezed and released repeatedly. This tidal flexing generates enormous internal heat. The friction produced by these movements warms Europa's interior, preventing its ocean from freezing solid, despite the extreme cold of space. Interestingly, Europa's orbit is also influenced by two neighboring moons, Io and Ganymede. These three moons are locked in a gravitational relationship known as a resonance. For every 4 orbits of Io around Jupiter, Europa completes exactly 2, while Ganymede completes 1. This gravitational rhythm continuously disturbs Europa's orbit, preventing it from becoming perfectly circular. As a result, tidal heating never stops. Without this resonance, Europa's orbit would eventually stabilize, tidal heating would decrease, and the hidden ocean might freeze over completely. But thanks to this delicate gravitational dance, the Moon remains active. This activity may also explain another mysterious feature of Europa, its extremely smooth appearance from space. Unlike rocky worlds with towering mountains and deep impact craters, Europa's landscape looks surprisingly flat in many places. Some scientists think this smoothness is caused by slow movement within the ice shell itself. The ice may behave almost like a very thick glacier. Over long periods of time, ice slowly flows, smoothing out sharp features and filling low areas. This gradual movement would erase many ancient structures, giving Europa its youthful appearance. The idea that an entire moon could behave like a giant glacier drifting above an ocean is one of the most fascinating concepts in planetary science. Yet, the evidence continues to support it. Additional observations from the Hubble Space Telescope have revealed another possible sign of ocean activity. water vapor plumes rising above Europa's surface. These plumes may erupt through cracks in the ice, releasing material from the subsurface ocean into space. If confirmed, they would provide an extraordinary opportunity for future spacecraft. Instead of drilling through thick ice, a spacecraft could simply fly through the plume and collect samples. These samples might contain salts, organic molecules, or other chemical traces from the hidden ocean. Such discoveries could help scientists determine whether Europa's ocean has the ingredients necessary for life. And that question, whether life might exist in this distant ocean, continues to drive scientific interest in Europa. Because if Europa's ocean contains liquid water, energy from tidal heating, and the right chemical ingredients, then in theory it could support living organisms. The dark ocean beneath the ice may therefore represent one of the most promising environments in the solar system for extraterrestrial life. But to truly understand what lies beneath Europa's frozen crust, scientists must first determine the ocean's depth, its chemistry, and how it interacts with the icy shell above. Future missions will attempt to answer these questions. And with every new discovery, Europa becomes less like a frozen wasteland and more like a hidden ocean world waiting to be explored. A silent moon orbiting a giant planet, an icy crust fractured by enormous gravitational forces, and beneath it all, a vast ocean concealed in darkness, an ocean that may hold secrets unlike anything we have ever encountered before. Beneath the frozen surface of Europa lies a world that scientists are only beginning to understand. While the icy crust of this distant moon captures most of our attention, the real mystery lies far below, deep beneath layers of frozen water, where a vast ocean may stretch across the entire moon. Understanding this hidden ocean requires imagining what Europa looks like from the inside. Planetary scientists believe Europa is made of several distinct layers. At the very center lies a dense rocky core composed of silicate minerals, similar in composition to the interior of Earth. This core likely formed billions of years ago during the chaotic early stages of the solar system, when countless icy and rocky bodies collided and merged together. Above this rocky core is where Europa becomes truly extraordinary. Surrounding the interior is a massive layer of water, some of it frozen, some of it liquid. Scientists believe that the total depth of Europa's water layer could reach 100 kilometers or more, making it one of the largest reservoirs of liquid water in the entire solar system. To put this into perspective, the deepest parts of Earth's oceans reach about 11 kilometers. Europa's ocean may be nearly 10 times deeper. This ocean does not sit exposed beneath the sky. Instead, it is sealed beneath an enormous shell of ice that may be anywhere from 15 to 30 kilometers thick. Above this frozen lid lies the strange cracked surface that spacecraft have observed. Between the surface ice and the rocky core, the hidden ocean may stretch endlessly in every direction. But how can such an ocean remain liquid so far from the sun? At Europa's distance, sunlight is incredibly weak. The moon receives only about 4% of the sunlight that Earth receives. Surface temperatures hover around minus 160 degrees Celsius, cold enough to freeze nearly any substance solid. Yet, Europa's ocean does not freeze completely. The reason lies in a powerful gravitational interaction with Jupiter. Jupiter's gravity constantly pulls on Europa as the moon travels along its orbit. because the orbit is slightly elliptical. The strength of this pull changes during each revolution. The result is a continuous stretching and squeezing of the Moon's interior. This process, known as tidal heating, generates enormous amounts of internal energy. Every time Europa flexes under Jupiter's gravity, friction is produced inside the Moon's interior. This friction converts mechanical energy into heat, warming the layers beneath the ice shell. Over millions of years, this heat accumulates. If enough heat is generated, ice at the base of the crust begins to melt. The result is a layer of liquid water trapped between the outer ice shell and the deeper rocky interior. In other words, Europa's ocean may exist not because of sunlight, but because of gravity itself. The gravitational forces acting on the Moon act like an invisible engine, constantly supplying heat to its interior. But tidal heating is not the only possible source of warmth inside Europa. Another contributor may come from radioactive elements within the rocky core. Just like Earth's interior, Europa's core likely contains small amounts of radioactive isotopes. As these isotopes slowly decay, they release heat. This process occurs extremely slowly, but over billions of years it can produce a steady supply of internal energy. Together, tidal heating and radioactive decay may be enough to keep Europa's deep ocean in a liquid state. Yet the ocean is not just a passive body of water. It may be an active environment, shaped by complex interactions between the ocean, the ice shell above, and the rocky interior below. At the boundary between the ocean and the rocky core, something remarkable may be happening. On Earth, the seafloor is home to hydrothermal vents, places where seawater seeps into cracks in the crust, becomes heated by magma, and then rises back into the ocean carrying dissolved minerals. These vents create entire ecosystems in the deep ocean. Even though sunlight never reaches these depths, life thrives around hydrothermal vents. Bacteria use chemical reactions to produce energy, forming the base of complex food webs that include worms, crustaceans, and fish. If similar vents exist on the floor of Europa's ocean, they could provide a crucial ingredient for life: chemical energy, because life does not necessarily require sunlight. All it requires is a source of energy, liquid water, and the right chemical building blocks. Europa may possess all three. The ocean could contain dissolved salts and minerals that originated from the rocky interior. Chemical reactions between water and rock could produce compounds such as hydrogen, methane, and sulfur molecules, substances that microorganisms could potentially use as energy sources. In this scenario, Europa's ocean might resemble Earth's deep ocean environments far more than scientists once imagined. But confirming this possibility requires understanding the chemistry of Europa's ocean. Observations of Europa's surface suggest that salts are present within the ice shell. Spectral data from telescopes indicate the presence of compounds such as magnesium sulfate and sodium chloride. These salts likely originated from the ocean below. When fractures open in the ice shell, ocean water may occasionally rise toward the surface. As it freezes, it leaves behind traces of dissolved minerals. Over time, these minerals accumulate on the surface, creating the patterns detected by scientists. This suggests that the ocean may not be completely isolated from the surface. Instead, there may be a slow exchange of material between the ocean and the ice shell above it. This exchange could be extremely important for potential life. On Earth, oceans remain biologically active, partly because nutrients circulate between the seafloor, the water column, and the surface. If Europa's ocean also experiences some form of circulation, it could help distribute energy and nutrients throughout the environment. Another important factor is oxygen. Life, as we know it, often depends on oxygen for metabolism. While Europa's ocean lies in darkness, oxygen could still reach it from the surface. Radiation from Jupiter constantly bombards Europa's icy surface. This radiation breaks apart water molecules, producing oxygen and hydrogen. The hydrogen escapes into space, while oxygen may become trapped in the ice. If surface ice containing oxygen slowly sinks downward into the ocean through cracks or melting processes, it could deliver oxygen into the water below. This process could create an ocean environment containing both oxygen and chemical nutrients, conditions that might support complex biological systems. However, scientists still do not know exactly how thick Europa's ice shell is. Some models suggest the shell may be relatively thin, perhaps only 15 kilometers in certain regions. Others suggest it could be thicker, possibly reaching 30 kilometers or more. Determining the thickness of this ice layer is one of the major goals of upcoming missions, because the thickness of the ice will determine how easily the ocean interacts with the surface. If the ice is thin and dynamic, cracks could frequently allow ocean water to reach the surface. If the ice is thicker and more stable, the ocean may remain sealed beneath a permanent barrier. Either way, the existence of a global ocean beneath Europa's ice would make this moon one of the most fascinating places in the solar system. The sheer scale of the ocean is staggering. If Europa's ocean truly exists, it may contain twice as much water as all of Earth's oceans combined. And unlike Earth's oceans, which are spread across the surface of a planet, Europa's ocean would completely surround the moon beneath its frozen crust. It would be a global sea hidden in darkness, a vast world of water trapped beneath ice. This ocean may have existed for billions of years. During that time, countless chemical reactions may have taken place between the water and the rocky core below. Energy may have circulated through hydrothermal systems. Minerals may have dissolved into the water, altering its chemistry. Over immense stretches of time, these processes could potentially create environments suitable for life. But even if life does not exist there, Europa's ocean still represents one of the most extraordinary environments known to science. It challenges our assumptions about where oceans can exist and how planetary bodies evolve. For centuries, humans believed oceans could only exist on the surfaces of warm planets. Europa suggests something very different. Oceans may exist beneath ice, hidden deep within frozen worlds scattered across the solar system. And if that is true, Europa may not be unique. Other icy moons, such as Enceladus and Titan, also appear to harbor subsurface oceans. Even distant dwarf planets may contain hidden water beneath their frozen crusts. The solar system may therefore contain many ocean worlds. Europa simply happens to be one of the most accessible. And as scientists continue studying this mysterious moon, the picture becomes clearer. Beneath the cracked surface of Europa lies a hidden ocean shaped by gravity, heat, and chemistry. An ocean that may hold clues to one of humanity's oldest questions. Are we alone in the universe? The surface of Europa is one of the strangest landscapes ever observed in the solar system. At first glance, it appears simple. smooth, pale, and quiet, but closer inspection reveals a complex and dynamic environment, shaped by enormous forces acting beneath the ice. These surface features provide scientists with the most important clues about what lies below the frozen crust and how Europa's hidden ocean might behave. Unlike rocky planets such as Mars or Mercury, Europa's surface is not dominated by impact craters. Most ancient surfaces in the solar system accumulate thousands of craters over billions of years as asteroids and comets collide with them. These scars usually remain permanently because there is little geological activity to erase them. Europa is different. The Moon contains very few large craters, which suggests that its surface is constantly being renewed. Instead of preserving ancient impacts, the ice shell appears to reshape itself over time. Cracks open, ridges form, and blocks of ice shift and refreeze. These processes gradually erase old features and replace them with new ones. One of the most striking features on Europa's surface is the presence of enormous linear fractures known as lineae. These dark streaks cut across the icy crust in long, curving paths that sometimes extend for thousands of kilometers. Some of them appear as thin lines only a few kilometers wide, while others are much broader and more complex. The formation of these fractures is closely related to the tidal forces produced by Jupiter. As Europa orbits Jupiter, the planet's gravity pulls on the Moon with tremendous strength. Because Europa's orbit is slightly elliptical, the intensity of this gravitational pull changes during each orbit. The result is a continuous stretching and squeezing of the Moon's interior. This process creates enormous stresses within the ice shell. When the stresses become strong enough, the ice cracks. These cracks can open and close repeatedly as the Moon flexes under Jupiter's gravitational influence. When water or slushy ice from below rises into these fractures and freezes, it forms ridges along the edges of the crack. Over time, repeated cycles of cracking and freezing create the long, double ridges observed across Europa's surface. Double ridges are among the most distinctive geological structures on the Moon. They consist of two parallel walls of ice, with a shallow valley between them. Some of these ridges can reach heights of several hundred meters and extend for hundreds of kilometers. The ridges appear to have formed gradually through multiple episodes of fracturing and refreezing. Another remarkable aspect of Europa's surface is the presence of regions known as chaos terrain. These areas look dramatically different from the rest of the Moon. Instead of smooth plains or linear ridges, chaos terrain consists of broken blocks of ice, scattered in irregular patterns. Many of these blocks appear tilted or rotated relative to their original positions. Some seem to have drifted apart before becoming frozen in place again. The entire region resembles a frozen jigsaw puzzle, in which the pieces have shifted and settled in new orientations. Scientists believe chaos terrain may form when heat from the subsurface ocean melts parts of the ice shell from below. When this melting occurs, the rigid crust above loses structural support. Large sections of ice can fracture and float on the slushy water beneath them. Over time, these floating blocks move slowly before the water refreezes and locks them in place. The resulting landscape preserves the chaotic arrangement of these displaced ice blocks. Chaos terrain may therefore represent locations where the subsurface ocean interacts most directly with the ice shell above it. If this interpretation is correct, these regions could provide the best opportunities for material from the ocean to reach the surface. Another intriguing surface feature is the presence of dark, reddish streaks along many of Europa's fractures. These colors stand out against the otherwise bright white ice of the moon. Scientists believe the reddish material may consist of salts or other compounds originating from the ocean below. When water from the subsurface ocean reaches the surface through cracks in the ice, it quickly freezes due to the extremely low temperatures. As the water freezes, dissolved minerals may become concentrated along the fracture lines. Over time, radiation from Jupiter alters the chemistry of these materials, producing the reddish coloration observed from space. The presence of these materials supports the idea that Europa's surface may be chemically connected to the ocean below. Radiation also plays an important role in shaping Europa's surface environment. Jupiter possesses one of the strongest magnetic fields in the solar system, and this magnetic field traps high-energy particles that form intense radiation belts around the planet. Europa orbits directly within these radiation belts. As a result, the Moon's surface is constantly bombarded by energetic particles. These particles break apart molecules within the surface ice, triggering chemical reactions that produce new compounds. For example, radiation can split water molecules into hydrogen and oxygen. The lighter hydrogen atoms escape into space, while oxygen may remain trapped within the ice. This radiation chemistry may have important implications for Europa's hidden ocean. If oxygen produced on the surface is transported downward through cracks or melting processes, it could eventually reach the subsurface ocean. This would provide an additional energy source for potential life. The interaction between radiation, surface ice, and the ocean below creates a complex chemical system that scientists are still trying to understand. Europa's surface is also unusually smooth compared with many other planetary bodies. Large mountain ranges are rare, and the landscape appears relatively flat across vast distances. This smoothness suggests that the ice shell may slowly flow over time, much like glaciers on Earth. Ice behaves differently from rock. Under the right conditions, ice can deform and flow gradually under its own weight. On Earth, glaciers slowly move across landscapes, carving valleys and reshaping terrain over long periods. A similar process may occur on Europa. The thick ice shell covering the Moon may slowly shift and flow as it responds to tidal stresses and internal heat. This slow movement could help explain why the surface appears so young and why many geological features appear stretched or distorted. The overall structure of Europa's ice shell remains one of the most important unanswered questions. Some models suggest the shell may consist of several layers. The uppermost layer could be extremely cold and rigid, while deeper layers may be warmer and more flexible. At the bottom of the ice shell, the ice may become partially melted, forming a slushy region where ice and water coexist. This structure would allow the outer crust to remain solid, while still permitting movement and interaction with the ocean below. Determining the thickness and structure of the ice shell is a major goal of future exploration. Scientists hope to achieve this through radar measurements that can penetrate the ice and reveal the layers beneath the surface. By analyzing how radar signals reflect from different depths, researchers may be able to estimate the thickness of the ice and identify pockets of liquid water within it. One of the missions designed to carry out this investigation is Europa Clipper. This spacecraft will perform dozens of close flybys of Europa while orbiting Jupiter. During each pass, it will collect high-resolution images of the surface and measure the structure of the ice shell using radar instruments. Europa Clipper will also search for plumes of water vapor that may erupt from the Moon's surface. Evidence for such plumes has been detected by the Hubble Space Telescope, which observed possible columns of water vapor rising hundreds of kilometers above the surface. If these plumes truly exist, they would provide a direct connection between the subsurface ocean and space. A spacecraft passing through one of these plumes could sample material from Europa's ocean without needing to drill through kilometers of ice. This possibility makes Europa one of the most exciting targets for future planetary exploration. The study of Europa's surface has already revealed a world shaped by powerful forces hidden beneath its icy crust. Cracks, ridges, and chaotic terrains all suggest that the ice shell is not a static barrier, but an active layer interacting with the ocean below. These geological clues provide the strongest evidence yet that Europa may contain a vast ocean beneath its frozen exterior. And, if that ocean exists, it may represent one of the most promising environments in the solar system for understanding how oceans form, how planetary bodies evolve, and perhaps even how life might emerge in the dark depths beneath an alien world. Beneath the frozen crust of Europa lies a vast ocean that scientists believe could contain more liquid water than all the oceans on Earth combined. But the presence of water alone is not enough to make an environment interesting for science or potentially suitable for life. What matters just as much is chemistry. The chemical composition of Europa's ocean could determine whether it is a sterile body of water or a dynamic environment where complex reactions occur over long periods of time. Understanding that chemistry has therefore become one of the most important goals in the study of Europa. To understand the ocean's chemistry, scientists first look at the materials that make up the Moon itself. Europa formed in the early solar system from a mixture of rock and ice. When the giant planets were forming billions of years ago, countless small objects collided and merged together in the region surrounding Jupiter. Some of these objects contained silicate minerals similar to those found on Earth. Others were rich in frozen water and volatile compounds. Europa likely inherited both. This means that its interior contains a rocky core surrounded by layers of water ice and liquid water. When water comes into contact with rock over long periods of time, chemical reactions begin to occur. These reactions can release minerals and dissolved salts into the surrounding water. On Earth, similar processes occur constantly at the bottom of the oceans. Water seeps into cracks in the seafloor, interacts with hot rock beneath the crust, and returns to the ocean carrying dissolved chemicals such as sodium, magnesium, and sulfate ions. Scientists believe something similar may be happening inside Europa. If the ocean rests directly on top of the Moon's rocky core, water may circulate through cracks in the rock below. As it does so, it could dissolve minerals from the rock and transport them back into the ocean. This process would gradually enrich the ocean with salts and other chemical compounds. Evidence supporting this idea can be seen on Europa's surface. Observations made by spacecraft and telescopes have detected unusual materials along many of the Moon's fractures and ridges. These materials appear darker and slightly reddish compared with the surrounding ice. Spectroscopic measurements suggest that these areas may contain salts, such as sodium chloride or magnesium sulfate. The presence of these salts indicates that water from the subsurface ocean may have reached the surface at some point in the past. When that water froze, it left behind traces of its chemical composition. Radiation from Jupiter later altered these materials, producing the distinctive colors seen today. This connection between the surface and the ocean below suggests that Europa's ice shell may allow some exchange of material between the two environments. Such an exchange could be extremely important for the long-term chemistry of the ocean. Another key ingredient for chemical activity is energy. On Earth, most ecosystems ultimately depend on sunlight as their primary energy source. Plants capture solar energy through photosynthesis, and that energy moves through food chains across the planet. But in environments where sunlight cannot reach, life can rely on alternative energy sources. Deep beneath Earth's oceans, entire ecosystems survive around hydrothermal vents on the seafloor. These vents release hot, mineral-rich water from inside the planet. Bacteria living near the vents use chemical reactions to produce energy. This process is called chemosynthesis. Instead of relying on sunlight, these organisms extract energy from chemical compounds, such as hydrogen sulfide or methane. Larger organisms, such as tube worms and crustaceans, then feed on these bacteria, creating complete ecosystems in total darkness. If similar chemical reactions occur inside Europa's ocean, they could provide energy for potential life. Tidal heating, caused by the gravitational pull of Jupiter, may keep Europa's interior warm enough to sustain hydrothermal activity on the ocean floor. When water interacts with hot rock beneath the crust, it could generate chemical compounds capable of supporting biological processes. In addition to chemical energy from the seafloor, Europa's ocean may also receive oxidants produced at the surface. The surface of Europa is constantly exposed to intense radiation, trapped within Jupiter's magnetic field. High-energy particles bombard the icy crust and break apart water molecules. This process splits water into hydrogen and oxygen. Hydrogen, being very light, can escape into space. Oxygen, however, may remain trapped within the ice. Over time, geological processes could transport some of this oxygen downward into the ocean. If oxygen from the surface mixes with chemicals rising from the ocean floor, the resulting reactions could create a powerful energy source for microorganisms. In this way, Europa's ocean might receive energy from both above and below. From below, hydrothermal systems could provide reduced chemical compounds, such as hydrogen and methane. From above, oxygen produced by radiation could act as an oxidant. The interaction between these substances could drive chemical reactions capable of supporting metabolism. Another important factor in ocean chemistry is salinity. Scientists believe Europa's ocean is likely salty. Dissolved salts lower the freezing point of water, which would help keep the ocean liquid even in extremely cold conditions. salty water also conducts electricity well, which is important for explaining some of the magnetic measurements recorded by spacecraft. When the Galileo flew past Europa in the 1990s, its magnetometer detected changes in the magnetic field around the Moon. These changes suggested the presence of a conductive layer beneath the surface. The most plausible explanation was a global ocean of salty water interacting with Jupiter's magnetic field. The exact composition of the salts remains uncertain. Some scientists believe the ocean may contain sulfate salts, similar to those found in certain terrestrial oceans. Others suggest it may be dominated by sodium chloride, which is the main component of common table salt. Determining the exact chemical makeup of Europa's ocean is extremely important. Different chemical environments can support different types of reactions, and therefore different potential forms of life. For example, environments rich in sulfur compounds might support microorganisms similar to those found near sulfur-rich hydrothermal vents on Earth. On the other hand, environments rich in methane or hydrogen could support entirely different metabolic systems. Europa's ocean may have been evolving chemically for billions of years. During that time, water may have continuously interacted with the rocky interior, dissolving minerals and altering its composition. Tidal heating may have driven circulation within the ocean, distributing heat and chemicals throughout the water. If the ice shell above the ocean occasionally cracks or melts in certain regions, fresh material from the surface may also enter the ocean. All of these processes contribute to a complex and evolving chemical system. Understanding this system requires careful analysis of the Moon's surface materials. Future spacecraft missions will attempt to measure the chemical composition of Europa's surface ice in much greater detail. By analyzing the spectral signatures of different compounds, scientists can determine which salts and organic molecules may be present. If organic molecules are discovered on Europa's surface, it would be a particularly exciting finding. Organic molecules are the building blocks of life. While their presence alone would not prove that life exists on Europa, it would indicate that the necessary ingredients for biological chemistry may already be present. One of the missions designed to investigate these questions is Europa Clipper. Europa Clipper will carry instruments capable of analyzing the chemical composition of the Moon's surface in unprecedented detail. It will also study the structure of the ice shell and search for plumes of water vapor rising from the surface. If such plumes are confirmed, they could contain droplets of water from the hidden ocean below. Analyzing these droplets could reveal the chemical makeup of the ocean itself. The chemistry of Europa's ocean is therefore one of the most important scientific mysteries in planetary exploration. If the ocean contains the right combination of water, energy, and chemical nutrients, it could represent a habitable environment, even though it lies beneath kilometers of ice in the cold outer solar system. The possibility that life could exist in such an environment challenges traditional assumptions about where life can survive. For centuries, humans believed that habitable environments required sunlight and warm temperatures. Europa suggests that life might exist in completely different conditions, far from the sun, hidden beneath ice, sustained by chemical energy and geological activity. If this idea proves correct, It would dramatically expand the number of places in the universe where life might exist. And it would mean that the quiet ocean beneath Europa's frozen crust could be one of the most important places to search for answers to one of humanity's oldest questions. Are we alone in the universe? Beneath the frozen crust of Europa lies an ocean that may be one of the most promising places in the solar system to search for life beyond Earth. Scientists have spent decades studying this distant moon because it appears to possess 3 ingredients considered essential for life as we understand it: liquid water, chemical nutrients, and a source of energy. Each of these elements may exist within Europa's hidden ocean. Liquid water forms the foundation of all known biological systems. On Earth, water acts as a solvent that allows chemical reactions to occur inside living cells. It transports nutrients, dissolves minerals, and provides the medium in which life's molecular machinery operates. Europa may contain an extraordinary amount of water. Beneath its icy crust lies a global ocean that could be tens or even hundreds of kilometers deep. This ocean may contain more water than all of Earth's oceans combined. Yet water alone does not create life. For biological systems to develop, water must interact with chemicals capable of supporting complex reactions. These chemicals may come from the rocky interior of the moon. Scientists believe that Europa's ocean rests directly on top of a silicate mantle and rocky core. When water interacts with rock over long periods of time, it can dissolve minerals and produce chemically reactive compounds. This process may occur continuously on the ocean floor. One of the most important types of reactions that could occur there involves hydrothermal activity. On Earth, hydrothermal vents are located along mid-ocean ridges where seawater seeps into cracks in the crust. The water becomes heated by magma deep below the seafloor, and then rises back into the ocean carrying dissolved minerals. These vents release chemicals such as hydrogen, methane, and sulfur compounds into the surrounding water. Instead of relying on sunlight, microorganisms living near these vents obtain energy by oxidizing these chemicals. This process, known as chemosynthesis, allows entire ecosystems to survive in complete darkness. Scientists believe similar processes could occur within Europa's ocean. Tidal heating, caused by the immense gravity of Jupiter, may keep parts of Europa's rocky interior warm enough to drive hydrothermal circulation. If seawater penetrates cracks in the ocean floor, it could become heated and return to the ocean carrying dissolved minerals and chemical energy. Such environments could provide ideal conditions for microbial life. In addition to chemical energy from the ocean floor, Europa may receive oxidants produced at its surface. The Moon orbits within the intense radiation belts surrounding Jupiter. High-energy particles bombard Europa's icy surface and break apart molecules of water ice. This process creates oxygen and other oxidizing compounds. Hydrogen atoms produced in these reactions are light enough to escape into space, but oxygen may remain trapped within the surface ice. If geological processes transport this oxygen downward into the ocean, it could react with chemicals rising from the seafloor. This interaction between oxidants from the surface and reduced compounds from the ocean floor could create powerful chemical gradients. Chemical gradients are extremely important for life because they provide energy that living organisms can exploit. On Earth, Many microbes derive energy by transferring electrons between oxidants and reductants. If similar chemical gradients exist within Europa's ocean, microorganisms could potentially use them to power metabolic processes. Another important factor in determining whether life might exist on Europa is the stability of the ocean environment. Scientists believe Europa's ocean may have existed for billions of years. During that time, tidal heating and radioactive decay within the Moon's interior could have maintained a stable supply of heat. This long-term stability would allow chemical processes to occur over enormous timescales. Even very slow biological processes could eventually produce complex ecosystems if they have millions or billions of years to develop. However, the extreme environment within Europa's ocean presents many challenges. The ocean lies beneath a thick shell of ice that may be 15 to 30 kilometers thick. Sunlight cannot penetrate this barrier, leaving the ocean in complete darkness. Temperatures near the ice-water boundary may remain extremely cold, while deeper regions near the seafloor could be warmer due to geothermal heating. Pressure within the ocean may also be immense. Because the ocean lies beneath kilometers of ice and water, pressures at the ocean floor could reach hundreds of times the pressure at Earth's surface. Yet similar pressures exist in the deepest parts of Earth's oceans, where life has adapted to survive under extreme conditions. In fact, many organisms on Earth thrive in environments once considered inhospitable. Microbial life has been discovered deep beneath the ocean floor, within Antarctic ice, and even inside rocks several kilometers below the surface. These discoveries have dramatically expanded scientists' understanding of where life can exist. If life can survive in such extreme conditions on Earth, it is possible that similar organisms could exist in Europa's ocean. To investigate this possibility, scientists are developing missions designed to study Europa in unprecedented detail. One of the most important of these missions is Europa Clipper. Europa Clipper will orbit Jupiter and perform dozens of close flybys of Europa. During these passes, it will collect detailed measurements of the Moon's surface, ice shell, and surrounding environment. Among its instruments will be cameras capable of mapping the surface at extremely high resolution. Radar systems will probe the thickness and internal structure of the ice shell. Spectrometers will analyze the chemical composition of surface materials. The spacecraft will also search for plumes of water vapor rising from Europa's surface. Evidence for such plumes has been detected by the Hubble Space Telescope. These observations suggest that columns of water vapor may occasionally erupt through cracks in the ice. If confirmed, these plumes could provide a direct pathway from the subsurface ocean to space. A spacecraft flying through a plume could collect tiny droplets of ocean water and analyze their chemical composition. This would allow scientists to study the ocean without needing to drill through kilometers of ice. If organic molecules or other complex compounds were detected in plume material, it would be an extraordinary discovery. While such findings would not immediately prove the existence of life, they would indicate that Europa's ocean contains the ingredients necessary for biological chemistry. Future missions may eventually go even further. Some scientists have proposed sending robotic probes capable of landing on Europa's surface and melting through the ice shell. These probes, sometimes called cryobots, would slowly descend through the ice until reaching the ocean below. Once inside the ocean, a small, autonomous submersible could explore the underwater environment. Such a mission would represent one of the most ambitious explorations ever attempted. The technological challenges are enormous. The probe would need to survive extreme cold, intense radiation, and immense pressure. Yet the scientific rewards could be extraordinary. Direct exploration of Europa's ocean could reveal an entirely new ecosystem hidden beneath the ice. Even if no life were found, studying such an environment would provide valuable insights into how oceans behave on icy worlds. Europa, therefore, represents more than just a distant moon orbiting Jupiter. It is a laboratory for understanding how life might arise in environments far different from Earth. The discovery of life in Europa's ocean would transform our understanding of biology, showing that life can emerge independently in multiple places within the same solar system. Even the discovery of simple microorganisms would demonstrate that life is not unique to Earth. Such a finding would have profound implications for the search for life beyond our solar system. Because if life can arise in the dark ocean beneath Europa's ice, then similar environments may exist elsewhere among the countless planets and moons orbiting distant stars. Europa's hidden ocean, therefore, represents more than just a scientific curiosity. It may be one of the most important places in the solar system for answering one of humanity's oldest questions: whether life exists beyond our own world. Deep within the outer solar system, the icy moon Europa continues to orbit the massive planet Jupiter every 3.5 Earth days. From a distance, the moon appears quiet and motionless, its bright frozen surface reflecting faint sunlight. Yet beneath that calm exterior, powerful processes may still be shaping the interior of this distant world. For scientists trying to understand Europa's hidden ocean, one of the most important questions is not simply whether the ocean exists, but how it behaves. An ocean beneath a thick shell of ice would not remain perfectly still. Just like oceans on Earth, it would experience currents, temperature differences, and internal circulation driven by heat and gravity. These processes could move water throughout the interior of the moon, transporting chemicals, energy, and heat from one region to another. Understanding this circulation is crucial. If the ocean is stagnant and isolated, chemical reactions may occur slowly and remain confined to limited areas. But if the ocean circulates actively, it could distribute nutrients and energy across vast distances, potentially creating a more dynamic environment where life could emerge. Scientists believe several forces may drive circulation inside Europa's ocean. The first of these forces comes from tidal heating. As Europa travels along its orbit, the enormous gravity of Jupiter constantly flexes the moon's interior. This repeated stretching and squeezing generates heat within the ice shell and possibly within the rocky mantle as well. This heat does not spread evenly throughout the moon. Certain regions may become slightly warmer than others, especially near the ocean floor where geothermal activity could occur. When water is heated, it becomes less dense and begins to rise toward the upper layers of the ocean. Meanwhile, colder water near the ice shell sinks downward. This movement creates convection currents. Convection is a powerful mechanism that can circulate water through large volumes of an ocean. On Earth, convection drives ocean currents that transport heat around the planet. A similar process could occur inside Europa, slowly moving water between the warm ocean floor and the colder ice boundary above. Over time, this circulation could mix the ocean's chemical components, distributing minerals from the rocky interior throughout the water. Another force influencing Europa's ocean may come from the rotation of the Moon itself. Although Europa rotates relatively slowly, completing one rotation every 3.5 days, the rotation could still influence the movement of water within the ocean. On Earth, the rotation of the planet affects ocean currents through a phenomenon known as the Coriolis effect. This effect causes moving fluids to curve as they travel across the rotating surface. If similar dynamics occur inside Europa's ocean, large-scale currents could develop beneath the ice shell. These currents might move water along the underside of the ice crust, slowly redistributing heat and chemicals throughout the ocean. The shape of the ocean basin may also influence circulation patterns. Europa's rocky interior is unlikely to be perfectly smooth. Instead, the seafloor may contain mountains, valleys, and ridges created during the Moon's early geological history. These structures could redirect water currents, creating complex flow patterns similar to those seen in Earth's oceans. Some regions may experience stronger currents, while others remain relatively calm. The interaction between the ocean and the ice shell above it could further complicate these circulation patterns. Europa's ice shell is not a static barrier. It is constantly being flexed and stressed by Jupiter's gravitational pull. This stress may cause the ice to crack, shift, and occasionally melt in localized areas. When this happens, pockets of warmer water from the ocean may rise towards the base of the ice shell. In certain regions, this upward movement of water could thin the ice above it. If the ice becomes thin enough, it may fracture or collapse, producing the chaotic surface features known as chaos terrain. In this way, the ocean's internal circulation may influence the geological appearance of Europa's surface. Scientists suspect that some areas of chaos terrain correspond to locations where warm water from the ocean interacts most strongly with the ice shell. These interactions could create temporary lakes within the ice shell itself. Instead of the ocean reaching all the way to the surface, water might accumulate in pockets trapped within the ice. These subsurface lakes could remain liquid for long periods before eventually freezing again or draining back into the ocean below. Evidence for such lakes has been suggested by radar observations and detailed analysis of surface features. If these lakes exist, they could provide a partial connection between the deep ocean and the surface environment. Another important factor influencing Europa's ocean is the presence of dissolved salts. Scientists believe the ocean is likely salty, similar to Earth's oceans. Dissolved salts lower the freezing point of water, allowing the ocean to remain liquid even at extremely low temperatures. Salt also increases the density of water. Variations in salinity throughout the ocean could create additional circulation patterns. Water containing higher concentrations of dissolved minerals may sink, while fresher water may rise. These differences in density could produce layered circulation systems within the ocean. The chemical composition of the water may therefore influence how the ocean moves and mixes. Over long periods of time, these processes could gradually distribute energy and nutrients throughout the entire ocean. This mixing would be extremely important if life exists within the ocean. On Earth, ocean circulation plays a critical role in sustaining ecosystems. Nutrients released from the seafloor are transported upward by currents, where they support microbial communities. These microorganisms form the foundation of marine food webs. If Europa's ocean circulates in a similar way, it could create environments where nutrients and energy become available to potential organisms. Another intriguing possibility involves the interaction between Europa's ocean and Jupiter's magnetic field. Jupiter possesses the strongest planetary magnetic field in the solar system. As Europa moves through this magnetic environment, the Moon's conductive ocean may generate electric currents. These currents could produce additional heating within the ocean. Although the amount of heat generated by this process may be small compared with tidal heating, it could still influence the dynamics of the ocean over long timescales. Scientists are still working to understand how these electromagnetic interactions might affect Europa's internal environment. Future spacecraft missions will attempt to measure these effects more precisely. One of the missions designed to study Europa in detail is Europa Clipper. This spacecraft will carry instruments capable of analyzing the Moon's magnetic environment, gravity field, and ice shell structure. By measuring tiny variations in Europa's gravitational field during flybys, scientists may be able to estimate the depth and density of the ocean beneath the ice. These measurements could reveal how water is distributed inside the Moon and whether large-scale circulation patterns exist. Radar instruments aboard the spacecraft will also attempt to probe the internal structure of the ice shell. These observations may detect pockets of liquid water trapped within the ice. Such pockets could represent temporary reservoirs where ocean water interacts with the ice crust. If the ocean beneath Europa is indeed circulating and exchanging material with the ice shell, it would make the Moon a far more dynamic environment than previously imagined. Rather than being a static, frozen world, Europa could possess an active internal ocean system shaped by heat, gravity, chemistry, and time. Over billions of years, this hidden ocean may have undergone continuous cycles of heating, circulation, and chemical transformation. These processes could create a wide range of environments within the ocean itself. Some regions near the seafloor may be warmer and chemically active due to hydrothermal processes. Other regions near the ice shell may be colder and influenced by materials entering from the surface. Between these extremes, the ocean could contain layers with different temperatures, chemical compositions, and currents. Understanding this complex environment is essential for evaluating whether life might exist there, because life does not simply require water. It requires a stable environment where chemical reactions can occur, energy sources are available, and nutrients can circulate through the ecosystem. Europa's hidden ocean may possess all of these conditions, but confirming that possibility will require continued exploration. Each new mission to Jupiter and its moons brings scientists closer to understanding what lies beneath Europa's frozen crust, and deep below that icy shell, in the darkness of an alien ocean. The forces shaping this distant world continue their slow and silent work. Deep beneath the fractured ice shell of Europa lies an ocean that may have existed for billions of years. Yet, despite decades of research, scientists have never directly seen this ocean. Everything we know about it comes from indirect evidence: gravitational measurements, magnetic signals, geological patterns on the surface, and complex scientific models. To truly understand Europa's hidden ocean, humanity must eventually explore it. But exploring Europa presents one of the most difficult challenges in the history of planetary science. Unlike planets such as Mars, where robotic spacecraft can land directly on the surface and begin operating immediately, Europa is protected by a thick shell of ice that may reach depths of tens of kilometers. Beneath this ice lies the ocean scientists want to study. Reaching that ocean requires solving several enormous engineering problems. The first challenge is distance. Europa orbits the giant planet Jupiter, which lies more than 700 million kilometers from Earth. Even the fastest spacecraft ever built require several years to reach Jupiter. Sending a mission to Europa therefore requires careful planning and long travel times. The second challenge is radiation. Jupiter possesses the strongest magnetic field of any planet in the solar system. This magnetic field traps high-energy particles, creating intense radiation belts surrounding the planet. Europa orbits directly within these belts. Any spacecraft approaching the Moon must survive extremely high levels of radiation. Electronics exposed to such radiation can malfunction or fail completely. Engineers must therefore design spacecraft with special shielding and hardened electronics capable of operating in this hostile environment. Despite these difficulties, several missions have already explored the Jupiter system. One of the most important was the spacecraft Galileo, which arrived at Jupiter in 1995. During its mission, Galileo performed multiple flybys of Europa and collected detailed images and measurements that revealed the Moon's cracked ice shell and possible subsurface ocean. Those discoveries transformed Europa from a distant icy moon into one of the most exciting targets for future exploration. In the decades since Galileo, scientists have been designing new missions specifically intended to investigate Europa in greater detail. One of these missions is Europa Clipper. Europa Clipper is designed to orbit Jupiter while performing dozens of close flybys of Europa. Instead of entering orbit around the Moon itself, which would expose the spacecraft to extreme radiation, the mission will repeatedly approach Europa, collect data, and then move away to safer distances. During each flyby, Europa Clipper will use a suite of scientific instruments to study the Moon. High-resolution cameras will map the surface in unprecedented detail. Radar instruments will attempt to penetrate the ice shell and measure its thickness. Spectrometers will analyze the chemical composition of the surface, searching for salts and organic compounds. Magnetometers will measure the Moon's interaction with Jupiter's magnetic field, which can reveal important information about the depth and salinity of the ocean below. Perhaps most excitingly, the spacecraft will search for plumes of water vapor rising from the surface. Evidence for such plumes has been detected by the Hubble Space Telescope. Observations suggest that columns of water vapor may occasionally erupt from cracks in Europa's ice shell, rising hundreds of kilometers above the surface. If these plumes are confirmed, they could provide a direct window into the hidden ocean. A spacecraft flying through one of these plumes could collect particles of water and ice ejected from the ocean below. By analyzing the chemical composition of these particles, scientists could learn about the ocean without needing to drill through kilometers of ice. However, even if plume sampling provides valuable data, scientists ultimately want to go deeper. Many researchers believe the most definitive way to study Europa's ocean is to physically reach it. This idea has inspired the development of specialized robotic systems designed to penetrate thick layers of ice. One concept is known as a cryobot. A cryobot is a robotic probe designed to melt its way downward through ice using heat. Instead of drilling mechanically, the probe slowly melts the ice beneath it, allowing gravity to pull it deeper into the crust. As the probe descends, it would carry scientific instruments capable of analyzing the surrounding ice and water. Once it reaches the ocean below, the cryobot could release a smaller robotic submarine known as a hydrobot. The hydrobot would then explore the ocean itself. Such a robotic submersible could search for hydrothermal vents on the ocean floor, measure the temperature and chemistry of the water, and photograph the underwater environment. If microbial life exists within Europa's ocean, such a mission could potentially detect it. Yet, building such a system is extraordinarily difficult. The ice shell above Europa's ocean may be tens of kilometers thick. A cryobot would need to melt through this entire layer, while carrying enough energy to power its instruments and communication systems. Communication with Earth would also be extremely challenging. Radio signals cannot easily travel through kilometers of ice and water. Engineers would need to design a relay system capable of transmitting data from the hydrobot to the cryobot, and then back to a spacecraft orbiting above the moon. Despite these challenges, research into cryobot technology is already underway. Engineers are testing prototypes in Antarctica, where thick ice sheets provide an environment somewhat similar to Europa's ice shell. These tests allow scientists to study how robotic probes might behave while melting through ice in extremely cold conditions. Another challenge facing future missions is planetary protection. If Europa's ocean potentially contains life, scientists must ensure that spacecraft do not accidentally contaminate it with microorganisms from Earth. Even tiny numbers of terrestrial microbes could disrupt the delicate environment scientists hope to study. For this reason, any mission designed to reach Europa's ocean must follow strict sterilization procedures. Spacecraft components must be cleaned and sterilized to eliminate biological contamination before launch. These procedures ensure that any life detected in Europa's ocean would truly originate from the Moon itself rather than from Earth. The search for life on Europa is therefore not just a scientific challenge, but also a technological one. It requires advanced spacecraft capable of surviving radiation, penetrating thick ice, and exploring an alien ocean beneath the surface of a distant moon. Yet, the potential reward is extraordinary. If life were discovered in Europa's ocean, it would represent one of the most important scientific discoveries in human history. It would prove that life can emerge in environments completely different from Earth's surface. Such a discovery would suggest that life may be common throughout the universe, because if life can exist beneath the ice of Europa, similar environments may exist elsewhere. Other icy moons, such as Enceladus and Titan, also appear to possess subsurface oceans. Even distant dwarf planets in the outer solar system may contain hidden reservoirs of liquid water. These worlds may represent an entirely new class of environments, known as ocean worlds. Europa is simply the most accessible example. By studying Europa, scientists hope to understand how oceans form inside icy bodies, how they evolve over time, and whether they can support life. Every mission to the Jupiter system brings humanity closer to answering these questions. Each spacecraft that travels across the vast distances of space carries instruments designed to reveal another piece of the puzzle. And beneath the frozen surface of Europa, hidden beneath kilometers of ice, an alien ocean continues to exist in darkness, an ocean shaped by gravity, chemistry, and time. An ocean that may hold secrets about life beyond Earth, waiting to be discovered. Beyond the frozen crust of Europa lies a hidden ocean that has transformed the way scientists think about where life might exist in the universe. For centuries, humanity assumed that habitable environments must exist on the surfaces of planets, where sunlight provides warmth and energy. Europa challenges that assumption completely. The moon's ocean lies sealed beneath a thick shell of ice, far from the warmth of the sun, in one of the coldest regions of the solar system. Yet despite this extreme environment, scientists believe the ocean may contain the fundamental ingredients required for life. Understanding why Europa could be habitable requires examining the conditions that make life possible. Life on Earth depends on several key elements. The most important of these is liquid water, which provides the medium in which biological chemistry occurs. Water dissolves nutrients, transports molecules, and enables the complex reactions necessary for living systems. Europa appears to possess an enormous reservoir of liquid water. Beneath its frozen crust lies a global ocean that may be tens or even hundreds of kilometers deep. This ocean could contain more water than all of Earth's oceans combined. The presence of such a large body of water immediately makes Europa one of the most interesting places in the solar system. However, water alone does not guarantee habitability. Life also requires chemical nutrients that organisms can use to build cells and generate energy. These nutrients typically originate from interactions between water and rock. Europa's internal structure likely includes a rocky mantle and core beneath the ocean. If water from the ocean comes into contact with this rocky layer, chemical reactions could occur that release minerals into the water. These reactions could produce compounds such as hydrogen, methane, and sulfur molecules. On Earth, similar compounds play a central role in ecosystems found near hydrothermal vents on the seafloor. In these environments, microorganisms obtain energy by oxidizing chemicals released from Earth's interior. Sunlight does not reach these depths, yet life thrives there. The discovery of these ecosystems dramatically changed scientific thinking about the conditions required for life. Before their discovery, most researchers believed that sunlight was essential for sustaining biological systems. Hydrothermal vent communities proved that life can survive entirely without sunlight by relying on chemical energy instead. If similar hydrothermal systems exist on the floor of Europa's ocean, they could provide a comparable energy source. Tidal heating generated by the gravitational pull of Jupiter may keep the parts of Europa's interior warm enough to drive hydrothermal activity. Water circulating through cracks in the rocky seafloor could become heated and return to the ocean carrying dissolved minerals. This process would supply chemical energy to the surrounding water. Another potential energy source may come from Europa's surface. The Moon orbits within the intense radiation belts surrounding Jupiter. High-energy particles constantly bombard the icy crust and break apart molecules of water. This radiation produces oxygen and other oxidizing compounds. Some of these oxidants may become trapped in the surface ice. Over time, geological processes such as cracking, melting, or convection within the ice shell could transport these materials downward into the ocean. If oxidants from the surface mix with chemicals rising from the ocean floor, powerful chemical reactions could occur. These reactions could provide additional energy sources for microorganisms. The interaction between oxidants and reductants is one of the most important drivers of metabolism in many organisms on Earth. Similar processes could theoretically occur in Europa's ocean. Yet, even if all the necessary ingredients for life are present, there remains another crucial factor: time. Life on Earth did not appear instantly. The earliest evidence for life dates back more than 3 billion years. During that time, complex chemical processes gradually evolved into biological systems capable of reproduction and metabolism. If Europa's ocean has existed for billions of years, similar processes may have had time to occur there as well. Scientists believe the ocean may have formed early in the Moon's history. As Europa cooled after its formation, tidal heating generated by Jupiter's gravity may have prevented the interior water from freezing completely. This process could have maintained a liquid ocean beneath the ice shell for billions of years. A stable ocean environment lasting this long would provide ample time for chemical reactions to occur and potentially evolve into biological systems. However, the conditions inside Europa's ocean are still largely unknown. The temperature of the water may vary depending on location. Near the ice shell, temperatures may remain close to the freezing point of water. Near hydrothermal vents on the seafloor, temperatures could be significantly higher. Pressure inside the ocean may also be extremely high due to the weight of the overlying ice and water layers. Yet similar pressures exist in Earth's deepest oceans, where organisms have evolved specialized adaptations to survive. Some species of bacteria and microorganisms on Earth can tolerate pressures hundreds of times greater than those at the surface. These discoveries suggest that pressure alone would not prevent life from existing in Europa's ocean. Another unknown factor is the thickness of Europa's ice shell. Some scientific models suggest the ice may be as thin as 15 kilometers in certain regions, while other estimates place the thickness closer to 30 kilometers or more. The thickness of the ice influences how easily materials from the surface can reach the ocean below. If the ice shell is relatively thin and dynamic, cracks may allow oxidants and other compounds from the surface to mix with ocean water. If the ice is thicker and more stable, the ocean may remain more isolated from the surface environment. Either scenario has implications for the potential habitability of the ocean. An ocean with strong chemical interactions between the seafloor and the ice shell may provide multiple energy sources for life, even if the ocean is more isolated. Hydrothermal systems alone could still sustain microbial ecosystems similar to those found in Earth's deep oceans. To determine which of these scenarios is correct, scientists are preparing new missions designed specifically to study Europa. One of the most important of these missions is Europa Clipper. Europa Clipper will orbit Jupiter while performing dozens of close flybys of Europa. During these flybys, the spacecraft will map the surface in high resolution, measure the thickness of the ice shell, and analyze the Moon's chemical composition. It will also search for water vapor plumes rising from the surface. Evidence for such plumes has been detected by the Hubble Space Telescope. If confirmed, these plumes could contain material from the subsurface ocean. A spacecraft flying through a plume could analyze tiny droplets of ocean water and determine their chemical composition. Such measurements could reveal whether the ocean contains organic molecules, salts, or other compounds associated with biological processes. While this would not immediately prove the existence of life, it would provide valuable information about the ocean's habitability. Future missions may go even further by attempting to land on Europa and analyze the surface directly. Some scientists have proposed robotic probes capable of melting through the ice shell to reach the ocean itself. Although such missions remain technologically challenging, they represent the ultimate goal of Europa exploration. Direct sampling of the ocean could reveal whether living organisms inhabit its depths. Even the discovery of simple microbial life would revolutionize our understanding of biology. It would demonstrate that life can emerge independently in multiple environments within the same solar system. This would dramatically increase the likelihood that life exists elsewhere in the universe. Europa, therefore, occupies a unique place in planetary science. It is not merely another moon orbiting a distant planet. It is a potential ocean world, hidden beneath kilometers of ice, where the conditions necessary for life may exist. And beneath that frozen crust, in darkness far from the sun, an alien ocean continues to move slowly beneath the ice, carrying within it the possibility that life may not be unique to Earth. At the edge of the Jovian system, the icy moon Europa continues its silent journey around Jupiter. From a distance, it appears simple, an almost perfectly smooth sphere of bright ice, marked by dark cracks that stretch across its surface like scars. Yet beneath that frozen exterior lies one of the most extraordinary environments scientists have ever discovered. Hidden beneath kilometers of ice, a vast ocean may extend across the entire moon. For decades, this possibility remained only a scientific hypothesis. Astronomers studying distant worlds had long suspected that icy moons could contain internal oceans, but direct evidence was difficult to obtain. Everything changed when spacecraft began exploring the outer solar system in greater detail. The mission that transformed our understanding of Europa was Galileo. During the 1990s, Galileo orbited Jupiter and performed multiple flybys of Europa. The images and measurements it returned revealed a world unlike any other. Instead of being covered in craters like most ancient planetary surfaces, Europa displayed long fractures, ridges, and regions of broken ice. These features suggested that the moon's surface was being reshaped by powerful forces from below. Magnetic field measurements provided an even more important clue. As Europa moved through Jupiter's enormous magnetic field, Galileo detected signals that indicated the presence of a conductive layer beneath the surface. The most likely explanation was a global ocean of salty water. This discovery fundamentally changed the scientific importance of Europa. Until that point, Mars had been considered the most promising location in the solar system for searching for life beyond Earth. After Galileo's findings, Europa quickly became one of the most compelling targets for astrobiology. The reason lies in the unique combination of conditions that may exist inside the Moon. First, there is liquid water. Water is essential for life as we know it, because it allows complex chemical reactions to occur. On Earth, every living organism depends on water at some stage of its biological processes. Europa's ocean may contain more liquid water than all of Earth's oceans combined. Second, there is energy. While sunlight cannot penetrate the thick ice shell, other energy sources may exist within the ocean. The immense gravity of Jupiter continuously stretches and compresses Europa as it travels along its orbit. This tidal flexing produces heat inside the Moon's interior. That heat may drive hydrothermal activity on the ocean floor, similar to the hydrothermal vents found in Earth's deep oceans. These vents release minerals and chemicals that microorganisms can use as energy sources. Third, there are chemical nutrients. Water interacting with the rocky interior of Europa could dissolve minerals and produce compounds such as hydrogen, methane, and sulfur molecules. These substances could support metabolic processes in microbial organisms. At the same time, radiation from Jupiter breaks apart water molecules on Europa's surface, producing oxygen and other oxidants. If these oxidants eventually reach the ocean below, they could react with chemicals rising from the seafloor, creating additional energy sources. Together, these factors suggest that Europa's ocean may contain the basic ingredients required for life. But confirming whether life actually exists there will require further exploration. One of the most important upcoming missions designed to investigate Europa is Europa Clipper. This spacecraft will orbit Jupiter while performing dozens of close flybys of the Moon. During these flybys, Europa Clipper will study the surface, measure the thickness of the ice shell, analyze chemical compounds on the surface, and search for water vapor plumes erupting from the ice. If such plumes exist, they could contain droplets of water from the ocean below. By flying through these plumes and analyzing their composition, scientists could obtain direct information about the chemistry of Europa's ocean without needing to drill through the ice. Future missions may go even further. Some researchers envision sending robotic probes capable of landing on the surface and melting through the ice shell using heat. Once the probe reaches the ocean, it could release a small autonomous submarine designed to explore the underwater environment. Such a mission would be extraordinarily complex. The probe would need to survive extreme radiation near Jupiter, penetrate kilometers of ice, and operate in a dark ocean under immense pressure. Yet the potential scientific reward is immense. If life were discovered in Europa's ocean, even simple microbial life, it would represent one of the most significant discoveries in the history of science. It would demonstrate that life can arise independently in environments completely different from Earth's surface. This would suggest that life may be common throughout the universe, because if life can exist in a dark ocean beneath the ice of Europa, similar environments may exist elsewhere. Other icy moons in the solar system already show evidence of subsurface oceans. For example, Enceladus ejects plumes of water vapor from beneath its icy crust. These plumes contain salts and organic molecules, indicating that an ocean exists beneath the surface. Another moon, Titan, may also contain a subsurface ocean beneath its thick, icy crust. Even distant dwarf planets in the outer solar system may harbor hidden reservoirs of liquid water. These discoveries suggest that oceans beneath ice may be common among icy worlds. Instead of being rare environments, subsurface oceans may exist on many moons and planets throughout the galaxy. Europa is simply one of the most accessible examples. By studying this moon, scientists can learn how such oceans form, how they evolve, and whether they can support life. The study of Europa, therefore, extends far beyond the moon itself. It represents a new way of thinking about habitability in the universe. For centuries, scientists assumed that habitable environments must exist near the surface of planets within a narrow region around a star known as the habitable zone. Europa shows that life might exist far outside that zone, hidden beneath ice, and sustained by internal energy sources rather than sunlight. If that is true, the number of potential habitats for life in the universe may be far greater than previously imagined. Across the galaxy, countless icy worlds may orbit distant planets and stars. Some of these worlds may contain oceans beneath frozen crusts. And within those oceans, chemical reactions may have been occurring for billions of years. Whether any of those oceans contain life remains unknown, but Europa provides one of the best opportunities to find out. The moon's hidden ocean continues to exist beneath its fractured ice shell, circulating slowly through darkness, warmed by gravity and shaped by geological forces that have operated for billions of years. For now, it remains unreachable, separated from us by distance, radiation, and kilometers of frozen ice. Yet each new mission brings humanity closer to understanding what lies beneath Europa's surface. And somewhere in that silent ocean, beneath the ice of a distant moon, answers to one of humanity's oldest questions may still be waiting to be discovered.